Yeah. Okay. So let me start with thanking organizers and for arranging for all of us to come here. And I looked at who is attending and thought that actually out of two recent things that I did, both may be interesting to different parts of the crowd. So I wasn't sure what to talk about, and thought maybe I will try to give highlights on both topics, and discuss details later. So let me. Yeah, is this working? Yeah. So there are two topics. One is on electron hydrodynamics in interacting electron systems, and the other is on related to the main topic of that session, graphene superconductivity. Does this work? Yeah, graphene superconductivity. Perfect. So let me start with hydrodynamics. So hydrodynamics, already discussed yesterday by Kamran Bendia and mentioned by others, is a transport regime where we don't have disorder, we don't have umklapp, we don't have electron phonon scattering, and transport is dominated by momentum-conserving collisions, and then electrons basically behave like a fluid, and so that's an interesting regime, widely studied recently. And so this is a joint paper with MIT undergrad who graduated already and moved up the state to Harvard. So with Sergei, we were interested in signatures of electron hydrodynamics. But maybe before we get into what we worked on, let me just do a more general introduction. So in electron hydrodynamics, what you expect to see is, first of all, that collisions assist transport. So when you increase temperature and collision rate grows, you okay, sorry, hopeless. Collision rate grows, then you okay. Yeah. Okay. Collision rate grows, the dissipation decreases, and this happens because your electron flow self-lubricates, and so this is an interesting regime where it's phenomenologically it's like conda. You raise temperature, and system becomes more conducting rather than more dissipative. And furthermore, in this regime, one can have conductance which is higher than ballistic conductance. And so we, in 2017, together with Hao Yu, who is attending this meeting, we identified constriction as a good geometry and proposed to do this measurement, and the experiment followed right away. And they indeed saw that if you take constriction and measure resistance through it, you see that there is a negative temperature dependence of resistivity. Resistivity drops as you increase temperature. I'm hesitating to, yeah. Okay, good. Resistivity drops as you increase temperature until you hit the temperature above which phonons kick in. So if you look at the low temperature part, look at the low temperature, yeah. low temperature part, you see the drop unimpeded by phonons. So there is experimental observation already back then, 2017, and confirmed recently by new experiments in gallium arsenide, that the temperature dependence in that hydrodynamic regime is contrary to what you expect from Fermi-liquid theory. Fermi-liquid would predict T square. Here, the temperature dependence is linear in temperature, and you see it pretty clearly already in this data, and even more clearly in the more recent data. So the challenge is to understand that. It's a non-Fermi-liquid behavior, and from that point of view, it fits the topics discussed in this meeting pretty well. It's a different kind of non-Fermi-liquid behavior because it's not a highly resistive state, it's a highly conducting state, but and as a result, you get linear temperature dependence for conductance and not for resistivity, and there is no disorder, it's disorder-free, and so it's not clear, whether there is any relation at all. But I thought it would be interesting to talk about it because there is a feeling that there may be some relation between this, T-linear behavior in hydro regime and T-linear behavior in these other exotic regimes that have been discussed and will be discussed in this meeting. So with that, we started thinking, how to describe hydrodynamics, and there is some background there. So first of all, one can think about collisions in a two-dimensional Fermi system and realize that collisions are dominated by head-on processes. So collisions are not like in a three-dimensional Fermi Landau Fermi-liquid, they're mostly head-on. And as a result, you get some emerging long-lived modes. Namely, if you think about what head-on collisions do, they efficiently relax even parity harmonics, modulation of Fermi surface, and don't relax odd parity harmonics. And so as a result, there is a hierarchy of excitations with different parity, which is different from how it is in a three-dimensional Fermi-liquid. There are long-lived odd parity harmonics and short-lived even parity harmonics. And in order to understand hydrodynamics, one needs to account for all of these harmonics together, rather than what we are doing usually, accounting only for density and current. Right. So that's the challenge. And before we get there, actually, what Sergei did, and that's a very nice analysis, and there is a concurrent work by Shankar Dasarma, similar results, so what's shown here is you want to see by a naked, but you want to see these long-lived excitations by directly, and what you do for that, you take two-body collision operator on the Fermi surface, and all the action is at the Fermi surface, and find eigenvalues and eigenstates, and you indeed find, just by direct diagonalization, you find that indeed even parity modes have normal T-square scaling for their lifetime with temperature. Temperature controls the width of the Fermi surface where all the action is happening, whereas for the odd parity, the lifetimes increase very rapidly as temperature goes down. And I mean, analytic theory from 2019 predicted T to the fourth scaling. So here we see something close to that. Yeah, so that's the background. Now, infinitely many soft modes means that there are some collective modes in the system in addition to the ordinary velocity mode and momentum mode that will be responsible for transporting momentum and producing dissipation, and so that needs to be understood, and that's what we set out to do. The approach is no time for details, but the approach is basically to integrate out the high angular momentum modes and derive effective conductivity for the for the m=1 harmonic, which is responsible for carrying current, the resulting conductivity is non-local, and one can derive a continued fraction expression for that conductivity, where gammas are these rates that we defined 3 slides ago. And so now basically the problem is very simple. You just need to take this continued fraction and analyze it k-dependence. K-dependence is important because it's a non-local conductivity, so it will scale as some power law, perhaps some power law of k. And so one needs to do an analytic study of that quantity as a function of k, as a function of temperature. And so that can be done analytically, luckily. And one gets indeed a linear t scaling for conductance, and also fractional power scaling for it as a function of length scale. Yeah, so that's it. One can also do it in a brute force kind of way. One can just take this continued fraction and, without doing any analytic analysis, simply plot it as a function of k, as a function of temperature, and you indeed see that there is in contrast to three-dimensional Fermi-liquid, where there would be Fermi-liquid hydrodynamics in the long wavelength limit and ballistic behavior in a short distance limit. Here is quite different. Here there is always ordinary Fermi-liquid in the long wavelength limit at the smallest scale, but there is a very large range of length scales opening up where there is this new fractional power dependence of conductance versus wave number, and linear rather than quadratic scaling with temperature. So that's.
Does the 5/3 come from the m=4 or from these? How do you get the 5/3?
So in a Fermi-liquid hydrodynamics, this would be k², because this would be just the inverse of Stokes operator, right? So there is additional -1/3 power that comes from from t to the 4th, basically.
m=4 or for this power equals
okay.
4 or 3, because you have.
Yeah, so you need to, as an input, you need to say how these things scale as a function of m.
Right.
Right. And we know how they scale as a function of m based on previous studies. They scale as m to the 4th.
Okay, you assume m to the 4th.
Yeah. And so if you put this together, and also, what we learned recently from the diagonalization of collision operator, you get that Kolmogorov kind of scaling.
This is all from solution both for
yeah, so this is essentially a classical transport problem. It's not even, there are many modes, but they are not yet coupled non-linearly. They are coupled just because they're transporting momentum all together and exchanging momentum with each other. So it's a linear response problem, but it's a very complicated linear response problem with infinitely many modes, all of which they have a hierarchy of lifetimes and hierarchy of k dependencies, and so it's a pretty complicated linear response problem for a hierarchy of modes. I mean, very nice that it describes linear t scaling already on this level, but surely, I mean, one needs to look in nonlinear effects and quantum effects and all of that, so that will come. Yeah, anyway, so I'm summary and probably also out of time. Yeah, sure, good. So yeah, so basically the summary is that this linear t scaling, which puzzled us for a long time, is now explained by that unconventional hydrodynamics, which is peculiar for two-dimensional Fermi-liquids, and I don't think it has an analog in three-dimensional Fermi-liquids, but for two-dimensional Fermi-liquids arises very natural and is pretty common. So thanks for that, and now this I will leave for questions. Okay, so now 5 minutes for superconductivity. Luckily, Andreas said all of the things that are in the introduction. So basically, in superconductivity, there are graphene superconductivity. There are superconducting phases observed at the boundaries of magnetically ordered phases. And so there is a feeling that these two things must be related, and superconductivity must be somehow superconducting pairing glue maybe should be somehow related to what's going on in the nearby magnetic phases. And so there is a lot of work by including many people in this room on trying to understand that. And so what I want to talk about, and also we did something on that. I mean, this paper with Andrei was trying to understand what he already mentioned during Andreas' talk. And then what I want to talk about briefly is this paper, which is taking a slightly different approach. So here we're not trying to invent a new pairing glue. We're trying to ask a question: can we, by looking at the phase diagram, infer something about Cooper pair kinematics, right? And the idea comes from comparing phase diagrams in you can see it most clearly here in graphene bilayer and an ABC trilayer that Andrea talked about. And you see that strangely in graphene bilayer, superconducting phase terminates abruptly at some point, whereas interactions and Fermi surface properties don't seem to change very much. You see that, and confirmation of that is that the interacting phases basically don't care. They're very, very smoothly, but the superconducting phase terminates abruptly. And this is also seen in the Caltech experiment, and there will be data later if you want to see that. So this now seems to be pretty common. And the suspicion was maybe, let me skip introduction. I think also a list of people whose work I should cite. But basically, the suspicion was that there is some kinematic signature that maybe distinguishes these two cases. And let's think about that. So if you have typical Cooper pair attraction, phonon mediated, for instance, then there is not much of a constraint on the scattering angle. This electron can scatter from momentum k to momentum k prime, and angle between k and k prime is unconstrained. Then for other pairing mechanisms, which are due to quantum critical soft mode, so for example, if this wavy line is a soft mode, then scattering will be mainly forward, because momentum change will be dominated by momentum carried by this transferred by the wavy line, which is very small. And then for other pairing mechanisms, k and k prime will be nearly opposite to each other. And that's the case, for example, for the textbook cases paramagnons. That's this diagram that was a long time ago introduced in the context of superconductivity of helium-3, but then later it appeared again and again. And here it appears very naturally for the IVC pairing glue. If you have valley, the inter-valley polarization of the IVC kind, then if we're near that instability, then that soft mode will produce exactly that type of attraction, where k and k prime will be mutually opposite. So there are basically three cases possible, and if you can now ask, can these kinematic types be distinguished by measurement? And so the observation is that under some conditions, if you are lucky, by studying how Fermi surface varies under changing parameters in the system, you can actually see signatures that allow you to tell one mechanism from the other one, and this will be illustrated in a second. So basically, the observation is that, yeah, almost done. Yeah, the observation is that if you think about how these three different pairing mechanisms respond to change of Fermi surface topology that may occur under parameters in the system varying, then they respond very differently, and you can identify the one that responds like seen in the data. And basically, the details are here. If you compare the ABC trilayer case and the bilayer graphene case, you find that in the second case, Fermi surface looks like three pockets, one in each valley, and then if you vary density, the topology of the Fermi surface changes with, if you take this Fermi surface and that Fermi surface and overlay them, which you need to do to understand pairing, you see that crossings appear between pockets here and pockets here, and I mean they're not real crossings because these Fermi surfaces are far apart in K-space, but for superconductivity you need to bring them together, and then superconductivity will occur, mainly on the Fermi surface, hot spots. And so if your pairing mechanism doesn't care about angles by which Cooper pairs scatter, this is not relevant at all. And let's say if there was some phonon-mediated superconductivity, it only cares about density of states. Density of states at Fermi surface doesn't change much upon this transition. But the pair scattering that involves back reflection changes a lot, because that superconductivity only occurs at the hotspots, which are these valley crossing points, and they disappear abruptly as you vary density. And in contrast, for ABC trilayer, the Fermi surface is angular. Each Fermi surface is, each pocket is single pocket, and if you now overlay them, you get, not angular, it looks like that, and you do get hotspots for IVC pairing glue-induced superconductivity, but they are robust. They don't disappear as you vary density, and that's consistent with what you see here. Furthermore, one can do more analysis. One can actually take known values for all these parameters for the band structure and draw lines at which this topological transition happens, and the Fermi surface is restructured from this to that. And surprisingly enough, with no fitting parameters, one gets a phase boundary that goes exactly through the superconductivity termination point. I can explain to whoever is interested exactly how calculation was done and what parameters have been chosen, but there was no fudging here. And the similar behavior is observed for the data from Caltech group, which is bilayer graphene on TMD with spin orbit, and similar Hamiltonian is quite different because there is strong spin orbit, as Andrea discussed. But the basic observation that superconductivity terminates at the point where Fermi surfaces are restructured, they lose. Each of them preserves the topology, but they lose this valley crossing point, and that indicates that that pair scattering in this case is almost certainly a backscattering rather than some kind of pair scattering that doesn't care about angles or small angle scattering. And so this is the main result. I mean, also to entertain you in the last 10 seconds, if you do a calculation, you find that superconductivity actually is enhanced before it disappears, because if you calculate effective coupling, you find that it's inversely proportional to the sine of that angle, and this angle becomes very small near, near valley crossing point disappearing. So there is an enhancement of coupling. And what you see is somewhat consistent with the data, because superconducting region tends to widen before superconductivity terminates. Of course, this is too early to, for a comparison. We need more data on that, but qualitatively it looks good. So yeah. So anyway, I think I already out of time. I already said everything I wanted to deliver. Basically, this is a new testable signature that allows to probe directly the Cooper pair scattering type. Thank you.
Thanks, Leonid. Questions? Yes, Anka.
So, Leonid, let me ask some questions on the superconductivity part, which I have not followed. The other part I know very well. So, you then say that it's the same question I asked Andrea, but I'm asking it differently. Because of where it's happening, this transition is playing a role, so it cannot absolutely be phonons in this particular case. That will be your viewpoint.
I mean, I'm sure phonons also present and they produce pairing. The question is, so there is some pairing due to phonons.
Okay.
Can it lead to something like that all by itself? Probably not.
The spin-orbit coupling part is very difficult to see how phonons should do.
Yeah.
So, but then, graphene superconductivity is pretty generic. Any experiment, as Andrea showed, rhombohedral, tri-layer, twisted bilayer, different people get different TC.
Yeah.
And it's this sort of mechanism that you're talking about, and I have a paper saying spin fluctuations also, spin fermion, is very fine-tuned, and I worry that we are going to get into this quagmire, something what happened in high TC, that we'll all have our theories specifically suited to specific situation, and we'll never come to an agreement. I'm just trying to avoid that.
No, I'm not claiming that this can rule out any mechanism in any system. I'm just showing that if we are lucky, we can find situations that can pinpoint exactly what the mechanism in the system is.
So what would disprove, what would falsify your theory? What experiment can Andrea or Pablo do which will specifically show that this is not what is going on?
Nothing can falsify my theory.
Wow.
But,
this is what I thought. I wanted to put you on the spot. This is exactly what I thought.
But
it's hard to see all over again.
So I want to first offer a falsifiable consequence. So I think that this mechanism would predict non-S wave pairing within a valley. So that some kind of P wave, even within a valley. Yeah. So that means that now these systems are extremely clean. They're in the clean limit. That would predict that if you add a little bit of disorder, non-magnetic disorder with scattering within a valley, that should destroy superconductivity very, very rapidly.
I don't call it falsified.
Yeah.
Call it confirm.
Yeah. No, I mean, in my mind, if you do that and you see that superconductivity is not affected deep into the dirty limit, that would falsify this picture. I think. So it's just
maybe with spin orbit one can do something along these lines. Maybe I'm not sure sigma z spin orbit will be sufficient, but maybe Rashba will.
Yeah. And I also had this question. If you go back to the phase diagram of the bilayer on WSE2, you had the bigger phase diagram. Yeah. Do you have any ideas about the SC2, the other phase? What?
No. Okay. So we are working on it. We have ideas. Not good enough to present here. But this phase is quite different because it is embedded into an ordered phase. So what you see here on both sides of that phase, it's an ordered phase, probably some numeric order. So this analysis that I presented is not so easy to do here. I mean, we're working on it. Here it's pretty straightforward because on one side, I mean, there is a phase boundary here, barely visible, but on one side it's a disordered system, and in this disordered system, we can do just band structure analysis, and that it hits the phase boundary exactly we expected to hit it. On the other side, I mean, it's a dashed line because, you know, we're not sure, we're continuing to the straight line, but we can't, you know, it's an ordered phase, so we don't know how to handle that. But from the disordered side, where we know the band structure, we can predict where superconductivity termination point will be, and, you know, it's there.
Hi. In the same spirit of trying to confirm or verify, you have a strong dependence on the hotspot angle, right? Wouldn't this also be strongly affected if you have strain or you apply strain in your sample?
Yeah.
And you know more or less which way it goes, right? Without restraint,
So strain, I mean, the only problem with strain, I mean, you need to think about it. I think the strain wouldn't by itself suppress backscattering, because strain is, you know, preserves inversion symmetry, so it won't by itself suppress backscattering. It will change
the angle, right?
Change angle, but it will not change qualitative behavior. But maybe something else will. That's a good point.
But if you change the angle, you change the C, no? According to your
because yeah. But I'm sure that will be seen.
Sure.
If I may come back to the first part, can we go to the plot of the eigenvalues for different harmonics, please? Yes, thank you. So first of all, should be there also a log, like T4 log T, or just T4?
There may be a log. I mean, we went back and forth on that, but let's not
I think there should be a log.
Yeah.
And also, I cannot help but notice that other exponents calculated numerically tend to decrease with the harmonics index. 3.9, 3.3. So do you understand why this is happening?
This is probably just transient. I mean, it will probably become T to the fourth going down. I mean,
but at the lowest temperatures, is it still T to 4, or it's 3?
No,
it's 4 minus something.
So numerically, it's very hard to go to low temperature. I mean, at low temperature, you can do analytic analysis, which is what was done in that, you know, paper 6 years ago. But that's the limit of low temperature. We were interested in how this develops at temperature of order Fermi energy. So there you really need to do numerics, and you see that this comes in pretty early. So it looks like happening.
Thanks.
You mentioned non-Newtonian hydrodynamics. I'm here, Leonid. So my question is viscosity not constant in real space in your picture?
Viscosity is scale dependent. So this power law, not power law in temperature, but power law in K, basically means that it's a non-Newtonian fluid in the sense that viscosity depends on the length scale. So this K to the 1/3 power here. I mean, take K square out. K square is just Navier-Stokes. K to 1/3 power law, that's a scale dependence of viscosity.
So it should also give an anomalous size dependence, no?
Anomalous
size dependence of the sample.
Size depends, yeah, exactly. So this is what these measurements are very good at. I mean, it has not yet been done, but let's say in gallium arsenide samples, one can tune the width of constriction in situ and presumably see this.
Thank you.
All right, last question.
Hi, yeah, just to comment on the previous question. So we've been doing numerics at lower temperatures. So there is a t to the fourth, just a slower onset as you indicated. So basically the higher the angular mode number, the longer it takes for it to hit. Like you need to go lower in temperature for it to hit t to the fourth. And I'm pretty sure it's just t to the fourth. And if there is any logarithmic, it's in log m, not log t.
Exactly.
So it's just t4. Yeah, just a comment on that. Thanks.
Yeah, no, I agree with this.
Probably very last question about the same. Am I right that this is all true for convex Fermi surface? For concave one, you don't have this physics.
Probably not. Yeah. So there should be some phase transition if you vary Fermi surface shapes, and for a while this will be robust, but then you'll probably come to some inflection point or something like that, and then the story will change. So,
right. Story will change. This is the question. Story will change into what? What's your? Or you don't know?
No one looked into that. I mean, so there is a paper by Achim Roche, which is somewhat related to that question, but it doesn't pose it the same way. But I mean, one should look.
Yeah, because this was the question. Does it go back to conventional T-square or? Okay,
maybe.
All right, maybe something to think about over the coffee break. So let's close the session. Thank you very much again, Leonid. And let's reconvene at 11:05.